Hello and welcome to the 10th episode of Delving into Academics. For those of you who have forgotten or maybe have never come across this podcast before, Delving into Academics is a podcast where various researchers from physics, biology and chemistry are all interviewed about their current research and also their life as an academic. For this episode, Professor Marialuisa Aliotta tells us a bit about her work on nuclear synthesis and how it relates to various processes in stellar evolution. Hope you enjoy it. Here with me today we have Professor Marialuisa Aliotta. She did her undergraduate in physics at the University of Catania in Italy. She then continued to do a PhD there and then went on to become an Alexander von Humboldt postdoctorate fellowship at the Ruhr Universität in Germany from 1999 to 2001. In 2001, she became a lecturer here at the University of Edinburgh, and then in 2008 a senior lecturer, then becoming a reader in 2013 and a professor in 2016. She does research in experimental nuclear astrophysics. Thank you for coming onto the podcast. It's fantastic to have you.
Thank you for inviting me.
So let's start out. What type of research are you doing currently?
Okay, so I study essentially the nuclear reactions that take place in stars, and we are interested in finding out where all chemical elements come from, where are they created, how, and so we study the processes that contribute to what we call the synthesis, the creation of these elements. And these processes, which are essentially nuclear reactions that take place in stars, are also responsible for generating the energy that makes stars shine. And this is what we study.
So what type of experiments are you currently part of that are studying?
I am a member of a collaboration which is called LUNA. The acronym stands for Laboratory for Underground Nuclear Astrophysics. And the laboratory itself is located in central Italy. It's an underground laboratory, and maybe I'll say something more about it later. But the collaboration is fairly international, and there are researchers from Italy, Germany, Hungary, and a group of us here from the UK.
Wow. So what types of experiments do you do in this underground laboratory, and why is it underground?
Okay, the reason why we do our measurements underground is because the reactions that we try to study are very rare processes. In a star like our sun, there is a lot of hydrogen, and so hydrogen is essentially protons, and these protons collide with one another, and most of the times the collision resolves in just a simple scatter, a bit like billiard balls. But occasionally two protons may fuse together and form deuterium, and then deuterium may capture another proton and forms helium-3, and two helium-3 nuclei may fuse together, and so in these kind of sequences of fusion processes you can then transform hydrogen into helium, so you have created a new element. Now, even though the sun is very hot, the temperatures of 50 million Kelvin in its central core, these temperatures translate in relatively small kinetic energy, so energy of movement, if you like, for these particles. And because these are charged particles, so two protons have positive charges and they repel each other, the chances that they can come close together at those energies are very small, and that's why not much happens. However, in the sun there is so much hydrogen that even though the probability for a single reaction to occur is very, very small, nevertheless the sheer number of protons that are there makes it a sizable process. Now, when we try and recreate these fusion processes on Earth at the same energies, so using similar energies as we have in the sun, again, it's very difficult to make two such protons fuse together. And so we aim to detect very feeble signals. And the reason why we go underground is to protect our experimental setup from the interference from, for example, cosmic rays that come from outer space. And if they hit our detectors, they will leave signals that are kind of bigger and more numerous than the signals we are interested in picking up from the reaction of interest. So by going underground, we reduce the number of cosmic rays that hit our detectors, and so we stand a better chance to pick up the signal that we're interested in.
Yeah, awesome. And it sounds so interesting that you are able to study the interior of stars this way and the types of reactions that go on in there. So what kinds of findings are you finding from doing these sorts of experiments?
In many cases, this collaboration, LUNA, which has now been operating for almost 3 decades, has really pioneered this kind of studies, because up until last year, this was the only underground laboratory of its kind in the world. So our collaboration has been really in a unique position to be able to do this kind of measurements really at the lowest energies possible. Now, one may assume, well, what is so difficult about going to low energies? If anything, I would expect to be difficult to go to very high energies where you need huge particle accelerators like people use at CERN, for example. Now, in our case, the problem is not so much reaching, obviously, the small energies that we're interested in, but it's connected to the fact that at those energies, the probability for two nuclei to fuse is very, very small. So our challenge is not so much in going to the lower energies, but in the fact that at those energies, if we want to see something coming out of our reaction, it becomes very difficult. Okay, so our challenge is really picking the famous needle in the haystack. Okay, so just selecting or observing something which is very rare, intrinsically rare, and so we need to get rid of as much background noise as possible. And so this collaboration has been able over the years to really measure some of these reactions at the lowest energies ever accessed, and so approaching more and more the energies at which these reactions take place in stars. And so we have been able to study processes that take place in our sun, and processes that take place in other stars during different epochs of their stellar evolution. And sometimes some of these measurements have really changed a lot about what we know, what we thought we knew about stars. And just to give you an example, years ago, I wasn't a member of the collaboration back then, but there was a reaction that my colleagues there studied, which eventually changed the age of the universe by 1 gigayear. It's a complicated story how they got to that final outcome and implication, but that just hinged on the measurement of one single reaction that also takes place in our sun to some extent, but it's more important for other types of stars. And still, that one reaction, what they measured, revealed that what was assumed previously wasn't quite right. And as an implication of that particular reaction, it turned out that the universe had to be 1 gigayear older. So that was quite a remarkable result.
Yeah, absolutely. I wouldn't have thought 1 gigayear is a lot.
It's a lot.
I mean, when you're talking about the universe, it's quite a big margin to then correct the age of the universe from just this one type of reaction. And so the reactions that then go on in this lab, how similar are they to the reactions that go on in the core of stars? Because I know the environments are quite different. Does it matter so much, or have you been able to replicate the reactions in the star quite well?
Clearly the environment plays a role and may affect to some extent what we measure in the laboratory. We cannot recreate obviously the interior of a star in the laboratory, but we can try to study these fusion processes at the energies at which they take place in stars. So the environment is not quite the same, but the energy that these particles have when they interact with one another, we try to replicate that as closely as possible. And typically doing measurements at higher energies is easier because the probability for a fusion becomes higher, and so you measure more reaction products. But when you go to lower and lower energies, this probability becomes smaller, and so the reaction occurs more rarely. So this is where we are facing a challenge, going to lower and lower energies. But this we can do because we have particle accelerators. We can tune the energy that we give to this beam of particles. So essentially, just to give you a quick overview, our experiments consist in shooting a stream of particles onto a target which contains the nuclei that we want the beam to interact with. And so, for example, we accelerate beams of protons or alpha particles, which are nuclei of helium. And then, depending on what kind of reaction we want to initiate, we use targets of appropriate material. So, for example, we may use targets containing carbon or containing oxygen, or we can use also gas targets rather than solid targets, and we can study reactions between, say, a proton and a gas, or an alpha particle and a gas, for example, neon or other gases. And so we then put detectors around the target to pick out the signals of the reaction products that have been produced in the reaction. So this is the general kind of schematic illustration of the experiment. And by tuning the accelerator, we can change the energy of the beam. Okay, so we can change the energy at which the two nuclei will interact, the nuclei in the beam with the nuclei in the target. We can change this kind of interaction energy, and we can study how the probability of this reaction changes as a function of energy.
Okay, wow, that sounds quite complex, but also quite simple when you break it down to what is going on into a star, and you can translate it into quite an elegant experiment that can be done here on Earth. It just sounds really amazing.
Yes, it's quite fascinating, and it's I like it as a research area because it also connects us to the universe at large and tells us something about our origin and place in the universe. So I find it a very fascinating field to work in.
Yeah, absolutely. And so from this experiment, where do you see it going? And will there be developments on Luna in the future, or in nuclear astrophysics and nuclear synthesis?
In Luna, yes, there is a major upgrade going on at the moment, in that we have recently, the collaboration has got some funds to buy a new accelerator, which will also deliver, for example, carbon beams. At the moment, the accelerator that we have can only produce protons and alpha particles. And these have been enough for many years, almost 3 decades, to study lots of different processes that take place in stars. But there are some processes that may involve heavier nuclei, for example, the fusion of 2 carbon nuclei. And these processes we cannot study with the existing accelerator that we have. But recently, as I said, we have got some money to buy a new accelerator, which is more powerful and also allows us to produce different species of ion beams. And so we will be in a position to study reactions that at the moment would not be possible. So this is a kind of imminent development at Luna. But also worldwide, there are plenty of things going on in this field. Perhaps most notably, and what people working in this area are more aware of, is the fact that there are lots of laboratories in the world for the production of radioactive nuclei, which are also very important for some stages of stellar evolution. But many of these nuclei are so exotic, they live so little that they don't exist on Earth. So they may be produced in a star as a result of previous reactions, and they may be very important because they themselves may interact with other nuclei and produce new things. But when we want to study those reactions on Earth, first of all, we need to produce those elements. If I want to study a reaction that involves protons or carbon, there is plenty. Okay, carbon is everywhere. We can take a pellet of graphite and we can produce a carbon beam. But if we are dealing with very unstable nuclei that do not normally exist on Earth, how do we do a reaction that involves them? So first of all, we need to produce those species and then accelerate them and then make them interact with some other nucleus so that we can study, certain reactions that they are involved in. So these facilities are called radioactive ion beam facilities. The first one was in Leuven-la-Neuve in Belgium. They started producing the first beam in 1990, so in the early 1990s, and that really opened up a completely new field in this area in nuclear astrophysics, so that of producing radioactive ion beams. And now there are many other laboratories in the world that are trying to do the same. And there are some big projects. So there is one in Europe here at FAIR in Germany, where again they will produce more intense radioactive beam facilities that they've been able to do so far. And another big project coming up in the States, FRIB, at MSU, Michigan State University, where again they are going to expand what they had previously and make it even better and bigger and be able to produce even more of these exotic species. But there are plenty other laboratories elsewhere. There is one in France, in Japan, in Canada, so there are many now laboratories where these beams can be produced.
Yeah, wow, it sounds like a very big international effort to study these types of beams. So what is the difference between studying a proton beam and then studying, as you say, they're moving to carbon and then the radioactive beams as well? Are you studying different processes that go on in the star or different stages within the star with these different beams?
Both. We're studying different reactions, obviously, because the kind of ingredients, the nuclei that interact are different, but also we're studying different stages of stellar evolution. So when a star is formed, because stars are essentially hydrogen and a little bit of helium, the first reactions that can occur are those of fusing hydrogen together to produce helium. When that stage has been completed, then helium can fuse together and produce carbon and oxygen. And when those nuclei have been produced, if the mass of the star is high enough so that it can heat up its core more and more, then also carbon may fuse and produce heavier and heavier elements. Now, the point is that once initial elements have been converted up to iron, it's no longer possible to fuse iron nuclei together and liberate energy. And this is because of a property of nuclei, which is called the binding energy per nucleon. Okay, we won't go there, but basically it means that if we have two iron nuclei and we try and put them together, they will not liberate energy. So this means that once a star has synthesized iron in its core, it's no longer capable of supporting the gravitational weight of the outer layers. So the star collapses on itself and then it explodes as supernova. During these explosions, other reactions can take place. And some people, up until recently, believed that, for example, during supernova explosions, it might have been possible to produce elements heavier than iron, which we observe, they exist in nature, through a series of neutron capture processes. So processes where neutrons are captured by existing nuclei and become something heavier. And then eventually, when these nuclei beta decay, they change some of their neutrons into protons, and so they change the chemical nature of the element. So what happens in this case is lots of these unstable and exotic nuclei may be produced, and different type of nuclear reactions take place, and heavier nuclei, heavier species that can be produced. Now, I said up until recently, people thought that supernova may be a site for this process, which is called the rapid neutron capture process, and it involves lots of exotic nuclei. But in fact, in 2017, I think you may be aware, and many of the listeners might be as well, there was a first discovery of a neutron star merger. So LIGO and Virgo detected gravitational waves from two neutron stars colliding with one another. And this event has opened up the so-called multi-messenger era in astronomy. And basically it has been possible to study this one event at lots of different wavelengths. And people have seen the fingerprints of elements heavier than iron, like platinum, and people say gold and so on. Okay, it's not like people have been able to really see the signature of gold, but nevertheless they've been able to observe in the spectra, the radiation observed by this event, that there are traces of these heavier elements. And so we now believe that neutron star mergers might be a good site for this process, rapid neutron capture process, that produces lots and lots of elements heavier than iron, and where obviously lots of exotic nuclei will be produced in the process. So by using different nuclei on Earth, we can study different types of processes. And normally these different processes take place at different stages of stellar evolution.
Wow, that sounds really cool. And that you can relate it to different stellar evolutions, almost like seeing the lifetime of a star without having to observe it for like millions and millions of years.
Indeed.
And especially with the tying it into the neutron star merger, because I know that would be an event that many of the listeners would have known about because of the first observation of gravitational waves. So when looking at these experiments, are you thinking of specific scenarios or looking at specific types of stars, or is it more of a general overview of the reactions in different
Sometimes we look at quite specific types of stars. And typically our studies are motivated by some questions in astronomy or astrophysics. Or, for example, a recent study we did was about trying to understand the composition of some presolar grains. Presolar grains are inclusions that are found in meteorites. So these are pieces of rocks that hit the Earth from outer space. And we can measure very, very accurately what these rocks are made of. And sometimes we find some inclusions, some granules within these rocks that show a composition that is very different from what we observe in our solar system. And that points to the origin outside of the solar system. So in other words, those grains must have produced somewhere else by other stars and then somehow got grasped somehow into our solar system, and eventually some of these rocks, as I said, reach us on Earth. Now, some of these grains, their origin has been puzzling people for quite some time, and there was one reaction in particular that was thought to be key to try and understand where these grains might have come from. And so we studied this reaction at Luna. This was a project of a former PhD student of mine. And we were able to solve this puzzle and to say where those grains were coming from. So typically, as I said, our research is motivated by very specific questions of what happens in some stars or where some grains come from, and by trying to study the reactions that we think are responsible for some specific effects, we can try and answer those questions.
Wow. So you say you answer specific questions. Is there kind of maybe a big overall question that you particularly are interested in or would love to focus your research on in these experiments?
The overall question is what I was mentioning at the beginning. It's really trying to understand where do these chemical elements come from, and also when we look at how abundant they are in the universe, they're not all the same. By far, hydrogen is the most abundant element there is out there in the universe, and then is helium, and then carbon and oxygen are third and fourth. Carbon is the fourth most abundant element. And then elements like, in fact, all the elements from carbon upwards to uranium, all taken together, they only contribute about 2% of all the matter in the universe. Everything else is just hydrogen and helium. So why is that? We want to understand why we observe what we do. So we want to understand where these elements come from, how they are created, and which stage of stellar evolution they are created, and why do we observe the abundances that we do. So this is the kind of bigger picture question that we try to understand.
Yeah, and that sounds like such an exciting question, such an important and big, physics question of the present times. Do you have an inkling of why more elements are more abundant than others?
Yes, we do have, of course, some general answers, and we understand why, for example, the abundance decreases almost exponentially up until iron, and then it's almost flat after iron. And this is because the processes that contribute to the synthesis of the elements up to iron are essentially fusion between charged particles. And so because these fusion processes occur by a quantum mechanical effect known as tunneling through the barrier, this effect has this kind of exponential dependency, and this is why the abundances of these elements decreases exponentially. Beyond iron, the processes that contribute to the creation of elements heavier than iron do not involve charged particles anymore. They involve the capture of neutrons, and then when a nucleus becomes unstable, it beta decays, meaning it changes one of its neutrons into a proton, and so it becomes a new element. So these processes are different, and it turns out that their abundance then remains more constant, even for heavier species. So we do understand some broad features, and we have a good physical basis on which we can explain what we observe. But as you know, the devil is in the detail. Very often there are some tiny little details that are a bit more puzzling, and then we don't quite know why things are the way they are. For example, another project that we're working at the moment is to try to understand the abundance of lithium. Now, lithium is a light element, and like hydrogen, helium, possibly a little bit of boron, this element was produced soon after the Big Bang. The Big Bang represents the origin of our universe as we know it. Okay, this is the kind of accepted theory. And during the early epochs of existence of our universe, some light elements were created. So we have protons, so hydrogen, a little bit of helium, and also a little bit of, obviously, deuterium. So hydrogen deuterium, which is a heavier isotope of hydrogen, helium, and a little bit of lithium. Now, if we look at the reactions that might have taken place in that epoch, we can figure out how much of each of these elements could have been produced back then. So we have a theory called Big Bang nucleosynthesis theory, okay, that allows us to predict the amount of deuterium, helium, lithium that would have been produced during the Big Bang. What we can do now is to observe very old stars which were formed billions of years ago, and try to find out what those stars are made of, how much hydrogen they contain, how much helium, how much lithium, and so on. And by studying the radiation emitted from these stars, we can figure out, what is the abundance of these elements on the surface of these stars. Now, because these stars were formed at the beginning, okay, these were formed out of the material of which the universe was made back then, okay? So we can have a direct observation of what was the composition of the universe back then by simply looking at the surface of these stars. And then we can compare what we observe with what the Big Bang model predicts. Now, much of this is in agreement, but For lithium, there is a problem. In fact, there are two problems for the two different isotopes of lithium. One is lighter, one is heavier. And here the predictions disagree, or rather the observation, okay? They don't match what is predicted by the theory. So why is that? And we're trying to now investigate more in detail the reactions that will have produced and destroyed the lithium to see whether maybe we got something wrong in our theory, and try to see whether we can now match what is observed. And this is, for example, another study that we are doing at Luna, specifically for the lighter lithium isotope, lithium-6, and this is still ongoing, so we want to see what we get and whether we are able to solve this existing discrepancy. So this is just an example of a specific case where there is still a lot of work to be done. Even though we understand the big picture, there are lots of details where we still need to find some answers.
Yeah, and I love that it's about finding out those details and why those nitty-gritty bits and pieces that we don't know yet, like why do they happen. And I love how these types of experiments can relate to the beginning of our universe and exploring more into that field, because I know there's quite a lot of unknowns in that beginning part of the universe. So it's really exciting to hear, especially with lithium. I just never knew that would have been the trouble element, so to speak. So,
there are others, but this is a very well-known case in our field. Yes.
Yeah, it's just so exciting to hear, and it seems like such a field where there's so much going on and there's so many areas that it can be applied to, and the research that's coming from this, like so many questions it can answer. So what is it about nuclear astrophysics that really interests you? Like, how come you chose to become a researcher in this field?
This was kind of accidental in a way. So when I was an undergraduate, at some point in my third year, I had to choose the kind of area I wanted to specialize in. And my choices back then were either nuclear physics or astrophysics. In the end, I thought, okay, at least the stars is something that I can see, so I'll go for astrophysics, and that's what I did. But then when I had to choose the topic for my master thesis, I heard, and that was, as I said, just accidental, I heard a seminar by a nuclear physics professor in our department who was telling us about this new field of research, nuclear astrophysics, that merged the two together, and as I said, aims at trying to understand, how stars are formed, live, and die, and also what elements they can produce inside. And I was fascinated, and I thought, oh wow, this is a fantastic opportunity to merge the two interests I had, to merge them together. And so then I went to Louvain-la-Neuve, where they were doing one of these very, very first experiments on radioactive beams. And so I took part in that experiment, and I reported about it on my thesis, and that's how I started. Now, funnily enough, though, when I think back, when I was a child, this had nothing to do with what I wanted to become, because I wanted to become a ballerina, so nothing related to science, really. But when I went to university, this topic really fascinated me, and I decided, this is what I want to do. I also liked life as an academic, so I thought, yes, if I manage, I would like to become an academic.
Exactly. I didn't really know about this field until I started doing this podcast. It does sound like a merger of two of my favorite fields as well,
okay.
like nuclear astrophysics. It definitely sounds really interesting, and there's a lot there, and it's so interesting to hear your story and like how you kind of came upon this field, and it's worked out brilliantly. So you mentioned that you wanted to become an academic, you really wanted the life of an academic, and now that you are and you do research, what is your favorite thing about being a researcher now?
I like the freedom that we have to choose the projects that we want to work on. This is great, because then it doesn't really feel much like work. You just enjoy what you do and you're keen to do it. And in particular, the aspect of being an academic, it's something that I really cherish, is the fact that we are really free to manage our time the way we want, pretty much. Of course, if I have to give some lectures, then I need to be here at certain times, certain days and so on. But I can otherwise manage my own time the way I please. So I can decide how I'm going to structure my day and what time I come in, what time I leave. And of course, very often when we go to various laboratories for experiments, we sometimes also have night shifts, or we work on a Saturday, on a Sunday. But because it's my choice, I'm happy with that. I wouldn't like to work in an industry where you really have to be there, 8 to 9 to 5 or 6, whatever. It's not the type of job I would I would like. But here I really feel that I have a lot of freedom, which is something I value very, very much.
Yeah, and I've heard from a lot of the researchers that I've had on this podcast, they also that is a repetitive or reoccurring theme. They love the freedom to be able to choose what they want to work on, just spend their days working on the problem that they're really interested in and gets them going.
Yeah, and there is also another element which is this international aspect of science, which I love, because it allows me to go to places, and I've spent time in different countries, and it's also nice to be able to really see firsthand how other people do things, how the working ethics and different environments and different also cultures. And so this is fascinating. I also like the fact that when I go to conferences pretty much everywhere around the world, I also tend to meet people from all sorts of different countries, and this international dimension is fantastic. It really makes you feel, oh wow, there are no barriers. And in fact, what I like about science is that really there are no barriers. There is no religious or political barrier. You just work on the same questions, on the same science. We're all motivated by the same things, and everything else doesn't matter. The color of your skin or your political ideas, none of this really matters. And this is something that I like. And then the other thing I like working at a university is the opportunity to work with young people all the time. This is wonderful. Of course, it makes me feel I'm growing older every time I have a new class, and they were born in 2000. I say, oh, it cannot be. But other than that, it really is a fantastic experience also to keep yourself up to date with the new technologies and the latest developments. So this is really, really good.
Yeah, and so with the international aspect, do you feel that really strengthens physics, like having that international cooperation?
Absolutely, yes. And okay, this may depend a lot on the research area you work on, but certainly in nuclear astrophysics and specifically studying nuclear reactions, you really need big pieces of equipment. So you need accelerators, which are very expensive. You need detectors, which are very expensive. So this is not a kind of research that you could do as a single individual. So you obviously need large groups, large corporations, and it's normally very helpful to be able to draw from different pools of expertise and also funding opportunities, because you need all of these.
Yeah, exactly. And with, I guess, different countries have those types of resources, and I just love how international and collaborative physics can be with these types of experiments, because as you say, they are just working on the same type of research, working on the same sorts of questions, and it doesn't matter the kind of other stuff. What matters is the science.
Yes.
And that I love that about physics, particularly with the youth. I mean, I've just finished second year currently, so I'm part of that. Does it inspire you, seeing or maybe supervising PhD students and master's students?
Yes.
You get lots of inspiration from their projects and from their ideas.
Yes. I also like to see these people, in perspective, to see that they still have everything in front of them in terms of their career choices and their path in life. And that I find fantastic, really fascinating, and to feel that you may make a difference in some cases, that is really very rewarding. So these sometimes I feel when I supervise students, when I mentor students. I also do quite a bit of mentoring, and this is really fascinating to see, you know, these young people coming to you for guidance, for support, for inspiration, for all sorts of reasons. And if you can really make a little bit of a difference for them, you feel, okay, that's been good.
Yeah, and so for the people that you mentor, supervise, and see at an undergraduate level, do you have any particular advice that you give out to them, like anything that you'd really want them to know at this particular time of their life, whether they want to go into research or whether they're just not sure yet?
I would say my advice would be to stay open to opportunities. Sometimes when I look back at my own career path, I realize that a lot of what I've been able to achieve has been triggered by my curiosity of also exploring different realities. So I was prepared to go abroad and to spend time away. It's not always been easy, because sometimes you really feel lonely, you feel disconnected from your roots, your family, your friends. So I'm not saying it's easy, but it really adds to your background, to the type of person that you then become. And certainly it can open up many more opportunities than if you always stay in the same place. So of course, having this ability to take up opportunities as they arise is often critical to your success. Of course, you need to be prepared. To have solid background knowledge and skills and so on. But this is only part of the story. Sometimes people think that they have to be the best. Not, you can be just good, but be more prepared than others to take chances, to take risks, to have the courage to go out there and see what else happens. And for example, I had some colleagues from my home university who weren't as prepared as I was to go abroad and maybe spend a period of research elsewhere. And so they struggled a lot more than to establish their own career eventually. So some of them managed with time, but some others had to leave research and academia altogether, because there is only a limited number of jobs available if you always stay in one place. So going out and exploring new opportunities is certainly useful.
Yeah, that's fantastic advice. Thank you. It's something that people should actually keep in mind, because especially speaking with different researchers and lecturers, there is a lot of movement in
Absolutely.
academia to different institutions and such throughout your career.
Yes.
Yeah. So, as you say, like, I guess being prepared for that more than others would give you a real booster, I guess.
Yes, and more opportunities, absolutely.
Yeah.
Of course, there is also downside, because, as I said, it's not always easy to pack and go and, you know, change country and culture and language and colleagues and friends. You know, it takes its tolls, and if you spend 10, 15 years doing this every 2 years, you know, it could be quite difficult. And this is especially true for those who may want to have a family, settle down, you know, and have a family. So of course you need to find the right balance. You need to sometimes compromise, but potentially you can have it all. Maybe not all at once, but you know, with time you can have everything you desire.
Yeah, absolutely. And it's just such comforting advice and inspiring advice to take opportunities and to go to different places and just work through your career. Yeah, so thank you. And so for the very final question, do you have an inspirational book or article for us that you'd really love to share?
Inspirational book, one of my favorite books of all times since I was a teenager, was a book by Richard Bach called Illusions. This author is probably best known for the Jonathan Siegel book, which is also great, and but I've always liked Illusions more, and to me that book speaks about freedom, and I absolutely love that book. I read it when I was 16, and it was fantastic. And I remember thinking when I finished reading the book that, oh, this is the book I would have loved to write. So that was, remained one of my favorite books of all times, even to these days.
Wow, that's fantastic, and I'm sure our readers would absolutely love to read it as well, and it will give them a bit of inspiration in their lives as well. So thank you for that recommendation, and thank you so much for being on this podcast. It's been amazing to chat to you about your research and about the advice and about your life as a researcher. So thank you so much.
Thank you.
So thank you for listening to this week's episode of Delving into Academics, and I hope you found it interesting. Please like, review, comment and subscribe wherever you're listening to this. And if you want to find out more about the researcher, I will have their university website page linked in the description. See you in 2 weeks for another episode.